Hi, Doctor. We are from Group 2, Session 1, and we will be presenting our Phase 2 assignment. My name is Lisa Jing. First, I will begin our assignment by explaining how to access the original audio signal in MANET. The audio file named s1g2.wav was given as part of the assignment. We use the audio read function to read the audio file. We check if the audio has more than one channel. Only the first channel is selected to simplify the analysis. A sample index vector n is then generated, and this index is converted to time value in seconds using the sampling frequency for time-based analysis of protein. Then let us listen to the original audio to understand its characteristic.
0125.
Salam sejahtera to Dr. Aini. My name is Lee Mei Hua from Section 1 Group 2. Hereby, I'm going to explain on how we design a filter to remove background noise from the given audio signal. Before we start our filtering process, we first sample the audio signal to convert it into a discrete time signal. The first 200 samples were plotted using a stem plot to visualize the raw digital data. So, why a stem plot is used? Because it is ideal for discrete signal as it shows each sample clearly. Moving on, we design a Butterworth bandpass filter to retain frequencies between 1500 to 2500 Hz, which is a typical speech frequency range. Then, we apply zero-phase filtering using this formula to avoid any delay or phase distortion in the signal. Proceed to step 1.2, which is suppress residual noise of the audio. To further reduce background noise, we subtracted 75% of the previously filtered version. This gave us a cleaner speech signal. We then normalize the signal to prevent clipping during playback. A pole zero plot was also generated, and we can clearly see that zero appears on the unit circles at the stop band frequency. This shows where signal's components are removed. Also, the poles appear just inside the circle to confirm the filter is stable. In step 2, we design a linear phase FIR bandpass filter using a Hamming window method. This filter removes the unwanted low and high frequency noise and retains the band from 300 to 3000 Hz, which is a common range frequency for speech. We then plotted the impulse response of the filter. It was symmetric, confirming the filter is linear phase, meaning it won't distort the shape of the signal.
My name is Wang. I'm from Section 1, Group 2. Actually, we undergo the convolution. The convolution is the internal function that's in the MATLAB. So we use the convolution to apply the convolution between the clean signal and the FIR filter impulse response. This simulated how an LTI system processes a signal over time. The convolution performed the convolution of the input signal as clean with the impulse response hash of the FIR filter. Same is ensuring the output signal has the same length as the input signal. Step 4 is the alternatively convolution method. We can directly use the filter that use the different equation of the filter. Since the FIR filter have no feedback, so we can set the A equal to 1 and the B equal to hash. The result of the white flip is the filter output, while the convolution is given more control and the filter is preferred for the real-time processing due to the performance. Step 5, plotting result. We use the function subplot and the plot to plot the result that the original signal and the after filtering signal. The plot of the original signal and the filtered signal in the time domain is useful to check it if the noise is removed or not. If by ensuring the signal shape is not disrupted and verifying the filter is efficiency or not, and time domain plot help the subjective quality analysis, especially when paired with the listening text. In this result that we used to, the top of the graph is before the filtering and the bottom of the graph is the after filtering. You can see the changes between the amplitude and the shape of the filtering and original signal. So based on this, we can see that after filtering that the result will become more clean and the noise will be removed. Also, but there is also still some noise that we cannot remove. This is because the noise and the signal must share the same frequency range. For example, the background noise from the fans or people talking can be in the same range of the human speech, that is around the 300 until 3400 Hz. This may be, if we want to try to remove the noise, we might also remove the part of the voice that we want to keep. And also, the noise is due to the wideband. This means it's spread across the many frequency. Or stationary, it means that it changes over time. This type of the noise are much harder to remove using just a simple FIR filter or IRR filter.
Hi, my name is LOOI from Section 1 Group 2, and in this assignment, I'm in charge of analyzing the stability of the FIR bandpass filter by computing its step transform and visualizing its poles and zeros. So first, we look at the MATLAB code. In step 6, we convert this step transform to Z-plane or ROC by using the sim toolbox in MATLAB. And after that, the second step, we plot the Z-plane by using a function Z-plane. And third step, we further convert the filter to zero pole gain form using TF to ZP function. And followed by the last one, reverse transformation with ZP to TF form to validate the filter structure. And after we run the code,
0125.
we will get this Z-plane. And then first we look at the poles. We have 64 poles in the unit circle at the origin, so indicating this is the a FIR filter, which 64 poles are all on the origin, and it's also a stable filter, which all the poles are in the unit circle. And then we will see all the zeros are mostly close to the unit circle to cancel certain frequency, and we have 6 another zeros and 6 outside the unit circle and 6 inside the circle.
My name is Lisa from Section 1 Group 2. Now I would like to explain step 7, which is from discrete time Fourier transform, DTFT, to spectrum. The variable m is set to 1024, which determines the number of frequency samples used to evaluate the frequency response. The REQZ function is then used to calculate the frequency response HF of the filter, defined by its numerator b and denominator a coefficient over m frequency points. The result W contains the corresponding angular frequency values. A new figure is created and the magnitude of the frequency response is plotted against the normalized frequency, which range from 0 to 1. The x-axis is labeled as normalized frequency, the y-axis shows the magnitude of the frequency response, and a title is added to describe the plot as the frequency response DTFT of FIR filter. This visualize is important for understanding how the filters behave across different frequencies and for verifying the filter designs.
In the next step, I will amplify the filter audio before playback. The audio was amplified using a gain factor to increase its volume for better clarity. To prevent creeping, we normalize the amplified signal so that the maximum value is limited to 0.9 of the full scale. Then we play back both the original and the amplified audio signal. The original audio S is played using the sound function, followed by a pause equal to its duration to allow full playback. After that, the amplified audio Y amplified is played, and the pause again for its duration to ensure it finishes completely. This allows us to clearly hear the difference in volume before and after the amplification.